Think your system like gin. If you only lift light weights, you don't get stronger. You just get comfortable. That's exactly what happens when you're loop trained on easy cases. So we introduce pressure. We add fixed judge and smart challenger. One defines the truth, the other raises the difficulty. This lesson shows how to build that tension without letting the system cheat. And hey, if you're serious about building really AI system like this, make sure you subscribe. This course will get more powerful from here and more interesting. And we have planned for more courses like this as well. I want you to think everything we have built so far as a one example, as a one real life application. Each lesson has added a component and capability, but nothing got replaced. It's all running underneath. If you need to revisit any part, check the playlist linked on top right corner appearing right now, or you can actually go to the GitHub example repo where all the lessons link has been provided. I will reference it again definitely before the lab. In the last session, we built observability that give us the run history, live artifacts, and a feedback surface. Now we are not guessing anymore. We know where the system is weak. So here is a shift. We are not improving randomly. We are applying targeted pressure based on observed weakness. We have seen row by row basis which cases failed, where mutation is absolutely needed. Same loop, no new force. So don't think this is a new system. This system has all components in place as they were. Observability already existed, mutation surface already existed, and evolution, it's already there. You're just making loop now harder to satisfy. I like to think this like an arena. A judge is a referee, an executor is a current champion, a challenger each sending stronger opponent, and the system only improves as long as the champion survives through the fight. This is critical. If the judge change, you're moving the goalpost. That's how the systems start gaming themselves. Correctness must stay constant. This is where the most people likely to get wrong. A bad challenger equal to random noise, and a good challenger equal to surgical pressure. It looks at easy bins, repeated patterns, and weak edge cases, and then create a harder version of exactly same scenarios. Let me share one of my personal experience. When we build system as a data engineer for our own organization, we had a 50 different version of this different feed processing data engineers. And trust me, most of them will at least been revised more than 25 to 30 times before they get to 99% accuracy. So it is very important to take a smaller step and let the judge and challenger keep fighting against each other and build a best use case scenario. If your system just fail more, you don't improve anything, you just stress it. And that's what we want: failure, mutation, adoption, and improvement. That is a perfect loop that keep going and improving the signaling with better score every time we process that loop. That's why I always do well the plateau breaking. No new client, no real learning. So lock this in. Self-challenging works only if judge stays fixed and challenger is intelligent. We'll see in hands-on lab how we can build that synthetic as well as the natural challenger. The executor is a force to adopt, and miss one of this and the whole loop collapse. Before we jump in, grab the GitHub repo. You will find the link below in description. We are going to trace this live. Now here is your 4-minute lesson. Open the CleanLoop challenger path. Don't just feed the code, think like an operator. Ask yourself, where are the harder fixtures generated? What signal used to detect the weaknesses? How the judge is protected from being modified? And slow that we discussed: challenge, generation, execution, and evaluation. This key insight should be stored. the system increase difficulty without touching the correctness. And that's the safety mechanism. Once you see that, you understand self-challenging loop. If this kind of deep dive is helping you to think differently, press the notification bell so you don't miss any next lesson or any new courses we release. So let's go on a hands-on lab now. So we are on the hands-on lab, and as usual, we will start with the judge here. Let's see the review. It's just the same old executor challenger arena, and then it shows the flow here. Now, the 4 important theories that I would like you to remind again. Judge and challenger are not the same tool. Always remember, the one is to validate and the other is actually in the arena to test itself. Fixed selection pressure is where the improvement makes meaningful. Never try to throw random permutations or the experiments. Yes, there are good cases for random experimentation as well, which adds towards the end to identify the edge and the boundaries. But when we are progressing towards the better maturity, the fix and selection process to very accurate pinpoint improvement over the data is always going to make better decisions. Good challenge is always targeted and not random, what we already discussed with the point number 2, and self-challenging create the curriculum pressure. So what is a curriculum pressure means? We identify subdomain challenges. For example, TEAT is aligned data, incorrect data, and all sort of things. And all those curriculum we define using various mutation playbooks. And therefore, we start with the basic curriculum and then we progress towards the higher end of curriculum. And that will also overlap on number 2 and number 3 we discussed, the fix in action and a good challenge data. Now, I would leave this for you to read. It's a very detailed document to read. We will see here how this works. Evaluation endpoint, that everything is provided here, so you will be able to understand how we actually working on those. So then now the binary checked registry. So whenever we are building that result set, we actually build the binary tree that help us to build the complex decision matrix. Now, other than that, the important thing is a difficulty ladder. Now here I have created a 5 level of different curricula, and you can see here what it does. Mild finance messiness. It's just a moving, breaking ISO, voids, status, spelling of whatever it is, but it's a very mild messiness. Obviously this is not going to pass the deterministic, but it's a still mild. Moderate finance messiness, mixed state format, DDMMYY, and all sort of stuff. The currency symbol, the currency code, and everything, which is slightly more difficult than number 1. Then number 3, hard finance, dispute invoices, free trial, complimentary, and all sort of stuff that probably make your system more complex to resolve this, because it's a business context that need to be understood, and very hard negative reversals. These are the hard positive and hard negative. 4 and 5 are really hard positive and hard negatives. If you are attempting number 4 and number 5, make sure you have a powerful LLM to solve. Most likely a lightweight LLM won't be able to solve number 4 and number 5. Also, to prepare for number 4 and 5, we need to have stronger hint mechanism, the skin mechanism, and a prompt mutation as well, which are not gonna cover in this particular use case. So we're gonna leave the 4 and 5 outside of the scope as of today. But if you want to expand this example into prompt mutation and other areas, you can certainly use number 4 and number 5 to get just to check how far you can stress this example. Now let's go back on our preview back again. I think all of these things are important. Please go and validate them. Also read in this order. It will help you to understand the flow that we discussed. Run is a very simple. what I'll do is I'll go on a clean loop. Currently, I think the dashboard is running, so I'm gonna stop the dashboard. Okay, and let's check the status. When we check the status, I think the status is pretty fine. Absolutely, we can see we got adjustment and finance invoices and then challenger files. We will actually create the challenger file ourselves as well. So let's go and delete those challenger files from input. Adversarial. So let's just delete this challenger files. Now, what we want to do is we already and I need to probably get this from the observability stack. I'll do that again, don't worry, but I'll probably gonna use this command, which is better. So I've deleted all the challenge manifestation and work vibe. And then I'm gonna create the 1, 2, 3, the labels that we discussed. So let's see how it works. So you can actually choose the labels you want. I have selected 3 adversarial label 1, 2, and 3. And by the way, they all are based on the labels that we saw are difficulty levels 1, 2, and 3. And I said the 4 and 5 we most likely gonna take some heavier LLMs, which we are not using in this case. We're just using simple phi. This 1, 2, and 3 would be able to handle pretty much easily. So we've got all the adversarial, and this is synthetic, by the way. So we create the synthetic data to challenge, and this is also a very powerful way of training your own loop. So now let's go back and train our loop as well, and then evaluate. So by evaluating, we will know what is working and what is not working. So we can see here, while evaluating, obviously we expected 8 unexpected, which are not fixed. So that's why it's a 13 by 14. We cannot fix everything, but we can fix many of them. And we can see the still needing mutation 85, still unresolved after mutation 0. So now all we're gonna do is we're gonna run the loop. By the way, the evaluate will only do the dry run. It won't do the full run. And now the loop is actually running and generating more data for us. It is right now generating the mutation because then, as anticipated, mutation needed 65 and unresolved after mutation 0. So it was pretty much successful. And if we can see here, we got very much here. And this is what mutations we recorded. And this all were generated after the deterministic pass. Obviously, because deterministic paths won't be able to complete them. So let's go and now validate our dashboard. I actually need to also run the dashboard command. Observe is the same as dashboard, just in case if you want to reprint what last run is, but observe will just reprint exactly what last run is. And this is now 8501 running. So I'm just gonna refresh it. And you can try two ways. This is the last run, always last run on top, but you can also select the current artifact for a last run, and you can see what we process. It will show you everything that what we have produced as a output, and it will also show us in data quality what we actually produce. So we can see how many rows deterministically been processed, adversarial mutation playbook, how the adversarial mutation playbooks has been processed. We can see what was anomaly reasons like unpassable dates on this invoices, and it will give you very much detailed report that what happened and how and where things got stopped with a very detailed traceability as well. So yeah, it's you can actually see on every every run. So these are all different runs of invoice 105, and this is how we can actually compare whether the invoice 105 failed before and whether the invoice 105 worked this time. And that's why what we previously discussed in observability, why it is important. So this is the overall idea which I give you for this judge self-challenging. And I think I messed up between number 4 and number 5, which I have to fix anyways, but I will fix our second in the GitHub so you guys have direct access to that. But other than those commands which are misplaced in 4, the exercises are pretty important, guys. From here, what we are looking at is something more serious. Earlier, we just saw that we send the data to LLM and get the mutation surface. But now it's a point of how we can actually improve our mutation surface, how we can self-generate those hints, how we can self-generate direction prompts, and lot more things. There are other areas which I would say when you're talking about the judge and challenger and arena, there are other areas which are not covered in this particular course, but keep an eye on my channel. I'm going to release a course on prompt mutation, and I'm going to release a course on behavioral learning by the loops itself. One, maintain a behavioral skill, and it mutate the skill to keep the learning in a longer run as a long-term memory. And the prompt mutation is also long-term to the operational memory perspective, and it also generates a lot of adversarial hints that how to handle different adversarial use cases. They both overlap. By the way, they all three overlap. They all three are different mutation surfaces. They all overlap. But with all of them three, we can actually have a long-term behavioral understanding and improvement and training. We have mutation surface by code, and we have also the mutation surface by prompt invocation. So these three will always make things better. All of my use case, all of my examples or the real life implementation are basically with all these three. Means there are very few where I have actually went to the reinforced learning. I have couple of agents where we have reinforced learning, but they are like very advanced use cases and generally not needed for day-to-day purposes. But having said that, this is more important to understand from a theoretical and example point of view, because you're picking up those things. But as I said, I'm going to have those 2 courses as well. And when we have all 3 courses, it will make a lot of sense that comes together, and you will be able to make really advanced self-improving agents. Doesn't matter whether it's a data agent or a stock agent or a trader or whatever you would like to make. But with these 3 capabilities and ability in your hand, you will be able to practically build any business case agent as you wish, with complex workflows, with reinforceable learning as well. So that's good. And I would suggest that please go ahead and implement this exercise as well. It will help you to understand the concept far better. Now let's go back on our presentation. And right, so now your loop isn't running, it's under pressure. And as I said, the adversarial pressure, we keep pushing them 1, 2, 3, 4, 5, and judge say fix, and the challenger keep pushing, and the executor has no choice but improve. That's how the real system evolve. Next, you go even further. And by the way, before I end this lesson, there are 2 different ways of evolution system. One, self with human observation, and one, self without human observation. And the both are very powerful techniques. As I said, when we have all 3, then we will also have a bonus lesson on human observed and human independent evolution processes. And they both are very interesting topics to discuss as well. But next, we go even further. We'll introduce best of and re-ranking. You have heard re-ranking in RAGs, where you get better candidates and you choose among those candidates. This is exactly the same concept, but we will choose between the correct mutations. We will choose between the better mutation for use cases. And so the system can compare multiple candidates before committing to a mutation. Make sure you are subscribed so you don't miss that, because it's really getting interesting from here. And I would really love to you to continue this whole course, and I'll see you in the next course as well. Take care then. Bye bye.